found the first m-1 principal components as the m-1 eigenvectors of S that are associated with the largest m-1 eigenvalues. Since S is symmetric, the spectral theorem states that we can use these eigenvectors to construct an orthonormal eigenbasis of an m-1 dimensional subspace of Rd. Generally, the mth principal component can be found by subtracting the effect of the first m-1 principal components, b1 through bm-1, from the data, thereby trying to find principal components that compress the remaining information. We then arrive at the new data matrix x hat, which is equal to x minus the sum of the bi transpose times x, which is equal to x minus bm-1 times x, where matrix X is a vector of x1 through xn, which is in d times n dimensional space and contains the data points as column vectors. bm-1 in this case is bi transpose, which is a projection matrix that projects into the subspace spanned by v1 through bm-1. Matrix X hat contains the information on the data that has not been compressed. We note that throughout this chapter, we don't follow our normal convention of collecting data x1 through xn as rows of a data matrix, but rather we define them as the columns of X. This means that our data matrix X is d by n rather than a conventional n by d. The reason for this choice is that the algebra works out a little bit more smoothly without the need to either transpose a matrix or redefine vectors as row vectors that are left multiplied into matrices. To find the mth principal component, we maximize the variance Vm, which is equal to the variance of Zm, which is equal to 1 over n times the sum of Zm mn squared, which is 1 over n times the sum of the bm transpose x hat n squareds, which is bm transpose s hat bm, subject to the constraint that the norm of bm squared is equal to 1, where s hat is the data covariance matrix of the transformed data set x hat equals x1 hat through xn hat. As previously, when we looked at the first principal component alone, we will solve a constrained optimization problem and discover that the optimal solution, Bm, is the eigenvector of S hat that's associated with the largest eigenvalue of S hat. It turns out then that Bm is also an eigenvector of S. More generally, the eigenvectors for S and S hat are identical, and we can find an orthonormal basis of eigenvectors for S and S hat. In fact, Vn is equal to Bm transpose S Bm, which is lambda m Bm transpose Bm, or lambda m. This means that the variance of the data, when projected into an m-dimensional subspace, equals the sum of the eigenvalues that are associated with the corresponding eigenvectors of the data covariance matrix. The MNIST dataset, digits dataset, I should say, contains 60,000 examples of handwritten digits 0 through 9. Each digit is a grayscale image that's 28 by 28. That is, it contains 784 pixels, so that we can interpret every image of this data set as a vector in 784 dimensional space. Each entry in the vector is going to be a 1 if it's dark and 0 if it's light. In the figure on the left, we have eigenvalues sorted in descending order of the data covariance matrix of all of the 8 digits of the MNIST training set. So we've gone through, we've picked out every 8, we've trained the data, and we've We picked out all these eigenvalues. In panel B, we look at the variance that's captured by those principal components that are associated with those eigenvalues. Again, we're looking at 784 dimensional space. And when we get even as few as 50, we've captured well over half of the variance, it appears. While the panel shows the 200 largest eigenvalues, we can see that once we get, again, past 50, but certainly when we get to 200, there is very little variance that's being captured by keeping additional dimensions. Therefore, most of the variance when projecting data into a subspace spanned by the corresponding eigenvectors is captured by only a few principal components. Overall, to find an m-dimensional subspace of RD that contains as much information as possible, principal component analysis tells us to choose the columns of the matrix B as m eigenvectors of the data covariance matrix S that are associated with the m largest eigenvalues. The maximum amount of variance principal component analysis can capture with the first m principal components is Vm, which is the sum up to m of the lambda m's, where lambda m are the m largest eigenvalues of the data covariance matrix S. Consequently, the variance lost by data compression through PCA is Jm, which is equal to the sum from capital M plus 1 to D of lambda j, which is equal to Vd minus Vm. And so the ratio Vm over Vd is the proportion of the variance that's captured, which means that the proportion of the variance lost is 1 minus Vm over Vd.